Hello everyone, this is Doug, and in this video I'm just going to briefly introduce to you chemical equations, the different parts of them, the different names of the parts, and what sort of information we get from chemical equations. First, I want to just remind you here, right, that a chemical equation just describes a chemical reaction, right? It just describes what's going on, what you had before, and then what you have after. What was the transformation, right? You just want to remember that a chemical reaction or transformation is when you rearrange the atoms. So in this video, at least, I'm not talking about nuclear reactions or physical reactions or transformations, just chemical ones. We're talking about the rearranging of these atoms here. And so here's a picture right up here where we have oxygen. This is just regular molecular oxygen, like the stuff that you breathe, right? O2. Notice that there's two oxygens attached to one another. And then we have over here, we have hydrogen. I'm not going to write in yellow because that's impossible to see, but those would be H2 molecules, right? They have two hydrogens, H2s. And what we have here in the middle is this is considered the reaction arrow. This thing is the reaction arrow. And this is supposed to be your dividing line between before the transformation and after. So what we're saying is that we have two H2 molecules, right? We have an H2 molecule here, an H2 molecule here, and we have one O2 molecule before. And then we're saying that after, we rearrange those, so now they're no longer attached to the same things, right? We took our Lego pieces, we broke down our Death Star, and we made a pirate ship. We've rearranged those pieces, and now we have something new, right? And now in this case over here on the right-hand side, I have two water molecules, two H2Os. H2Os. And so we can represent any reaction this way and saying like, oh, look at all these different parts and here's how we're going to rearrange them. But of course, this is going to get cumbersome if we're drawing a whole bunch of little spheres of things to represent a chemical transformation. And so what we do is we just try to abbreviate that into a chemical reaction. And so what we say, right, is that, okay, well, I have some H2s. How many of those H2s do I have? Well, I have two of them. So this is going to say I'm going to have two H2s. And it looks like I have an O2. And that's what I had beforehand, but then after they react with one another, then I got two water molecules, right? And that's what we're just trying to abbreviate exactly what we just saw there, right? So that's what a chemical reaction is at its core. It's basically a recipe for the change that occurred. Just like you look up a recipe for like making a cake or cookies or, stir fry or anything, right? You have your list of before things that you need to mix together. Something happens, and then afterwards you have something new, right? You have 24 cookies or a cake or whatever it is. But I want to get more into the nitty gritty of like what we call these different parts and how these are arranged. So here's a more chemically looking equation. And so I'll just write the names of these things so that we don't have to keep on saying C6H12O6, but this is a formula for this could be glucose. In my mind, it's glucose, but it could be any of the isomers, but that's a whole other conversation. O2, we know is just oxygen, just the elemental oxygen. CO2 is carbon dioxide. And H2O, everyone knows, is water. So now if I look at this equation, right, just before, right, I was saying that everything on the left-hand side is the before, everything on the right-hand side is the after, right? This is the big dividing line for the transformation. The stuff on the left-hand side is sometimes called the reactants. It's also sometimes called the starting materials. Or even the reagents. So there's kind of three names for the left-hand side stuff, right? Any of these things. The right-hand side stuff is just called the products. It's the stuff that is produced from this transformation. So the products, nice, easy, just one word. Now, we do have all of the formulas, like I was saying before. We've got glucose, we've got the O2 molecule, we've got the CO2 carbon dioxide, and the H2O water. But in this equation here, I also have these numbers in front. I have a 6, a 6, and a 6, and in front of this one, there's no number really written, but if you don't see anything there, you just assume there's a 1. That is a 1 there, that we're saying 1. These things that I underlined in purple here, right, these are the coefficients. and I won't draw a line to every single one of them, but the numbers in front of the formula that are of a normal height, they're not subscripts or superscripts, they're just regular sized. Those are the coefficients. And they tell you how many of the following species there are. Right, whether that chemical species is an element or a compound or whatever it is. So coefficients is an important word to know. When we talk about balancing equations, we talk about coefficients a lot. And you can translate this chemical formula into a sentence, right? What this is saying to me, what this recipe is saying to me, is that for every, so when you mix one glucose molecule and 6 oxygen molecules, you produce 6 carbon dioxide molecules and 6 water molecules. Right, that's what this equation is telling me. When I have 1 glucose molecule and 6 oxygen molecules, I produce 6 CO2s and 6 waters. And that's talking about like on a molecule level, right? One molecule to another molecule. Of course, we don't really do a lot of reactions molecule by molecule, right? Reactions occur with huge amounts of things, right? If you're going to burn a bunch of sugar, this is a combustion reaction, but we'll talk more about that later. But if you're going to do this reaction, this combustion reaction, you don't just burn one molecule, right? You burn like an insane numbers that we don't really have good words for, that are just so large. And so another way that you can read this sentence, I'm not going to rewrite this all out, but I'll put it in sort of parentheses here in red, is you could also read this as when you mix 1 mole of glucose molecules and 6 moles of oxygen, you produce 6 moles of carbon dioxide and 6 moles of water. And that is a much more representative size, right? Remember that a mole is 6.022 times 10 to the 23rd of those molecules, right? It's a much larger amount. That's usually how we do our record keeping, is in terms of moles. And so we're going to talk more about the fact that these are also mole relationships in future videos. But basically, chemical equations, right, they just describe the before and after of a chemical transformation. Now here's one more, because I have something else to add. This is still, right, the reactants are on the left, the products are on the right-hand side. We still have some coefficients here, right? We have the two HIs. There's just one in front of everything else, apparently, so only one real coefficient aside from one. But I did want to point out that I do have these other things here, right? I have these things in parentheses. Sometimes you'll see these, sometimes you won't. Sometimes I'll ask you to put them, sometimes I won't. But these are supposed to be the states. All this stuff in blue is the state. And the states just tell you what state that reagent is in at the time, right? So, and they stand for something. So S, as you might guess, stands for solid. This sort of scripty L thing. This scripty, whoa. Let's see if I can draw that again. The scripty L stands for liquid. So you kind of do that like loopy thing. The G in parentheses, as you might guess, stands for gas. And then AQ is the other one, and we'll talk more about this again in the future, but AQ here just stands for aqueous, which means dissolved in water. So you may see these abbreviations after the chemical species in an equation, right? So what this is saying is that apparently this lead carbonate is soluble in water. And now I don't actually know if lead carbonate is soluble in water, but let's just say that it is. It might not be. But let's just say that lead carbonate has an AQ after it. That means this is dissolved in water. And then the hydroiodic acid is aqueous. That's also dissolved in water. And so what we're saying is that when we mix those two solutions together, what you form is this lead iodide that is a solid. It's a yellow solid that drops to the bottom. But you also make some bubbles. You make some carbon dioxide that's a gas, and this gas bubbles on out. And you make some more water, which is a liquid. And we know that we just put an L here because you don't say that water is dissolved in water. That doesn't make sense. It just is more water, so we just put a liquid here. And we'll talk more in the future about how we determine what these states likely are. We kind of need to know some temperatures, for example, of things. But we'll talk more about that in future videos. So I just want you to get this, just supposed to be a brief introduction about what you see when you see these chemical equations, what these different abbreviations mean, and the terminology behind them, right? Reactants versus products. We have coefficients that are in front, not superscripts or subscripts, that are actually in front of the chemical species to help balance it out. And we'll talk about balancing equations more in the next video. So study up. Good luck.